Hello, my dear students, and welcome to the second part of our Chapter 4 discussions. I want to just cover a few, or actually seven, I think, 14 to 21, maybe that's 8 slides by starting where we left off with reactions in water and frequently made a separate chapter. This chapter includes acid base reactions, and that brings up the question of what's an acid and what's a base. Things that we measure on the pH scale, which you learned incorrectly is between 0 and 14, and the lower the pH, the more acidic it is, and the higher the pH, the more basic it is. Another way to say that is the less acidic it is. Now, the reason for that is, I want you to remember two things. pH is defined as minus the log of the hydrogen ion concentration. Okay? And these brackets mean concentration of, and we'll get to that as we get to the end of this chapter and solution stoichiometry. But two things jump out about this equation. It's an inverse relationship. So the lower the pH, or let's put it this way, the higher the hydrogen ion concentration, the lower the pH. So that's why low pH means high acid. Low pH means high acid. Okay? Because it's an inverse relationship right here with that negative. And then the other thing I'd like you to notice is it's also a log relationship. That's a base 10 log. And that means for every number difference, the difference between pH 1 and pH 2 is not that one has double the acid, it has 10 times. Similarly, the difference between pH 3 and pH 4, pH 3 has 10 times the acid as 4. And going, for example, from pH 2, pH of your stomach, to pH 4, that isn't a 1, 2, or 4-fold difference or anything like that, or even a 10-fold or a 20-fold. That's a 100-fold. That's a 10 times 10-fold difference because we went down 2 pH units and we're talking about a log scale. Okay? Now, to define an acid. Several times you've heard me say it's an acid, produces H+, that makes it an acid. And that's the way S.A. Arrhenius defined acids is, and that's, I don't know how you pronounce his name. It's got like a SV together, Svante Arrhenius, but I do know he was Swedish and he won the Nobel Prize for chemistry in 1903. But that was significant because the Nobel Prizes are awarded in Stockholm, and he was the first person from Sweden to win the Nobel Prize. So this was a great point of national pride for a Swedish chemist to win the Nobel Prize. He just said, you're an acid if you produce H+, and if the concentration goes up, the pH goes down. Okay? They're proton donors. This H+, hydrogen ion, is also referred to as a proton. And the reason being, of course, it's element number 1, has 1 proton, 1 electron, and if you remove the electron from the hydrogen atom to produce the hydrogen ion, what you're left with is a proton. An extremely small, extremely mobile, extremely reactive species. So these are going to become significant in many reactions, especially I'm afraid I'm showing my prejudices as a biochemist. Anyway, this is, I guess you would say, the classical definition. He also defined a base as something that is a hydroxide or OH minus or hydroxide anion donor. Don't forget, this OH minus is a polyatomic ion, and these stay together. I will say we're going to discuss acids and bases in more detail in the second semester of chemistry, where you work with weak acids and strong acids and have to use a quadratic equation to solve for concentrations. We're not getting to that this first semester. Now, Bronsted-Lowry said, you know what, this doesn't work for all the things that turn our litmus paper blue or pink. Litmus paper turns blue in base when the pH is greater than 7, and it turns pink, I don't know that I would call it red, when the pH is less than 7. And by the way, this P stands for minus the log of. So if you're going on in the medical field, you'll deal with PO2 and PCO2 and other values all the time that are concentrations converted to the reciprocal or negative log because it makes them easier to work with. So, he defined bases as substances that increase or donate hydroxide ions. Bronson and Lowry defined them as that because if you have an OH, what's it going to do? As soon as it finds an H+, these are going to combine to form HOH, which I'm going to be writing water that way for this particular screencast, which is H2O. Okay? So, OH minus is a proton acceptor, but in a slide or two, I looked over it, but I don't remember where it is, but it's coming up. In a slide or two, you will see, and I'll make a distinction in proton acceptors. Very important in biochemistry and the life sciences and working with weak acids, of which water is one. Because remember, I said these reactions go both ways, and water will break down into OH minus plus H plus. As soon as it does, it goes right back, and it does so. Well, we'll talk about equilibrium and that later, but an approach to equilibrium as well in kinetics, but it happens at a rate of 10 to the minus 7th, or gives you a concentration of this H plus of 10 to the minus 7th molar. We'll talk about that in the last part of the chapter. That's why the problems I'm giving you are not from your book directly, because they assume you've read the entire chapter and are applying all the different concepts in the chapter at once to solve a specific problem. I'd like you to go through them one at a time. So, the proton concentration, if I do minus the log of 10 to the minus 7th, the log of 10 to the minus 7th is negative 7, and minus that is what? 7, which is pH 7, which is neutrality, because the amount of acid produced is equal to the amount of base produced in pure water. And so that's where pH 7, a neutral pH, comes from. So in this case, water is both an acid and a base. You may have seen that thing in high school. People think it's funny to put out, beware of dihydrogen monoxide, which is, I guess, a IUPAC formal name for water. No one calls it that. The trivial name is suitable. water, but it is an acid. Yes, it's a weak acid. It produces protons by definition, by both Arrhenius and Bronsted-Lowry. Okay, Bronsted, for purposes, I mean, they were working a little bit after Arrhenius. He won the Nobel Prize in like 1903 or 1913, I forget exactly. But these guys were working, Bronsted and Lowry. Bronsted was a Danish, as you can tell from the name, Johannes, Johann, like Johann Sebastian Bach. He was working, you know, I think he died in the mid 40s around World War II, but he was a Danish chemist. And Lowry, I want to say Thomas Martin Lowry, he was a British chemist working about the same time. They simultaneously kind of worked on this. He died right before World War II. But, you know, this is like in the 30s and 40s they were doing their work. And they, I don't believe, won Nobel Prizes, but we used the Bronsted-Lowry definition of an acid as a proton donor and the Bronsted-Lowry of a base as a proton acceptor. So in this case, this is a base by both Arrhenius and Bronsted-Lowry definition, I guess, except that in this case, it's just an ionic species that does accept a proton to form water. Anyway, quickly, there's some acids you should know. Common strong acids, hydrochloric, hydrobromic, and hydroiodic acids. Chloric acid, HClO3. We also use perchloric acid. Well, there it is, the next one, HClO4. And nitric acid and sulfuric acid, which can donate 2 protons, but only the first one. It's H2SO4, and dissolved in water and put into solution, it produces H plus HSO4 minus. And that happens, and that dissociation from the neutral species to the H plus. So my concentration of H plus went up, my pH went down. A very, very acidic solution, very strong acid. That happened 100%. Okay, HCl. Let's take our HCl. It's HCl. You put it into water. It's a gas normally. You just dissolve it in water. You can only dissolve it up to about 37%, but concentrated HCl is about 37%, about 12 molar, but we'll get to molar at the end. Dissociates to H plus Cl minus. Okay, aqueous. Sometimes those state functions are important. So these are the strong acids, and these are really the only strong acids. They usually make people memorize them, but the ones we commonly encounter in the lab, at least the teaching lab, perhaps more in a research lab, are hydrochloric, perchloric, less so, nitric, and sulfuric. So these 4 are sometimes included in a list of the strong acids because you can find them and you can identify them. It's easy to pick them out in the lab. This one has a yellow top. Nitric acid has a red top. Perchloric acid, sorry, you won't be able to see it, has a white top. I'm going to erase that though. And hydrochloric acid has a blue top when you see them in the lab. So these strong acids dissociate completely. That's what makes them strong. The weak bases don't the weak acids only partially dissociate. For example, let me just go on. This is a weak acid. This dissociates into H plus SO4 2 minus. but it doesn't do so completely. When you look at this in the water, you'll see that I don't know what the Ka for this reaction is, but let me just throw a number out. I don't know if it's real or not. 90% of it will be in this form, and only 10% will be dissociated, for example. Okay? Or less. 99% and 1%. It just depends. It also depends on what other ions are present and the concentration. There are all kinds of effects that affect this reaction here. But the point is, it doesn't dissociate completely. Just the strong acids do. The strong bases do as well. Let me go to purple. Strong bases are things like sodium hydroxide. You know it as Li. Potassium hydroxide has also been historically referred to as Li. And less commonly, because it's expensive, lithium hydroxide, rubidium hydroxide, and cesium hydroxide with the group 1 bases. Some of the group 2s form strong bases. Calcium, strontium, barium hydroxide are pretty common ones, but there are lots of other weak bases. Ammonium hydroxide comes to mind that do not dissociate completely. Let's move on and talk again about that. Oops, I'm going the wrong direction. That proton donor. You know, in biology, we have many what I call amino groups hanging off of sugars, amino sugars, hanging off of proteins, hanging off of even lipids, and certainly hanging off of the DNA bases. And sometimes they're just written this way, but it's a nitrogen connected to the rest of the molecule with 2 hydrogens. But it is a Bronsted-Lowry base because it can bind to a third one. This nitrogen has electrons that attract the weak proton, H+, such that at one point they may actually bond and form a tight bond. Now this gets a plus charge on it. Sometimes we write that NH3+. But that is a weak base because it's soaking up the protons and raising the pH. It's not raising the pH by producing a base or OH minus. It's raising the pH by accepting the protons. It's a proton acceptor. So here's a reaction between ammonia. If you take ammonia, which by the way is a gas, and you bubble it through water, you form a solution of ammonium hydroxide, NH4+, that's the ammonium ion, OH minus. I should not have put the plus there. NH4, OH, which dissociates into NH4+ and OH minus. They're opposites. They come together. And when you dissolve this in water, some of it stays together and some of it comes apart. And then once some of it comes apart, some of it even, this turns into these 2 species. And then these 2, go ahead and do that. In fact, see how now we started writing this as a reversible reaction. My point is, right now, if I take water plus ammonia, we do it by bubbling through it, we'll make this compound ammonium hydroxide, which partially dissociates into ammonium ions and hydroxide ions. And this hydroxide ion is what raises the pH. Okay? Because at a high pH, you have low H+, and high OH minus. At a high pH. In other words, basic solution. It's basic because you have very low hydrogen ions, because you have very high hydroxide ions. This is an acid-base reaction without your typical acids and bases, okay? In this case, water is your acid because it donates a proton to NH3 plus. When it gives up one of its protons, what does it become? OH minus. It becomes this species. This water turns into this species, and the proton goes where? Well, it's attached to this ammonia, but now that gives it a positive charge, and we form ammonium ion. Ammonia is a gas. When you buy ammonia at Walmart, you are buying a solution of water that someone has bubbled ammonia through. It's a gas at room temperature and pressure. You can see the tank cars or the little tank trailers carrying anhydrous ammonia. In fact, they're made right there in DeWitt, and they scare the hell out of me because they have liquefied ammonia because they've been able to keep it under pressure. But if that were to be released, you would have ammonia gas, and then you should just run until it dissipates and goes away, or spray it with lots of water. That being said, this ammonia is a gas. The ammonia in Walmart is a solution of ammonia dissolved in water, bubbled through water to form this substance, ammonium hydroxide. Very powerful smell, very powerful effect on your nasal epithelia, and it also, when you buy it, may have some detergent and some perfume added, even perhaps some color added. However, we want to look at these reactions where we mix an acid and a base. They're called neutralization reactions, and a neutralization reaction produces water and a salt. Let's look. Hydrochloric acid reacts with sodium hydroxide. This is an acid, strong acid. This is a strong base. But I'm going to do the dance, okay? I'm going to have my chloride move from the hydrogen to pair with the sodium, and I'm going to have my hydroxide move from my sodium to pair with my hydrogen in the hydrogen chloride or hydrochloric acid. So now, and that's why I would have written this HOH. We no longer have an acid, we have water, and we have a salt, in this case sodium chloride. And if we write our complete ionic equation, this strong acid dissociates completely into hydrogen ions and chloride ions. And this sodium hydroxide, this strong base with the group 1 metal, sodium, dissociates completely into sodium ions and hydroxide ions. Well, what does an H plus and an OH minus do as soon as they see each other? They get together to form water. And remember, when we write the complete ionic equation, this is our chemical or molecular equation, balanced chemical equation. This is our complete ionic. If we remove our spectator ions, our ions present on both sides of the equation, so that's a totally legitimate mathematical operation, remove our sodiums, what we're left with is H plus OH minus come together to form water. And that is our net ionic equation. EQN for abbreviation. EQN equation. Now, when you mix, since this is reactions of acids, a metal plus an acid, you frequently produce hydrogen. I have some examples of that. But here is another reaction where if you're using carbonic acid or carbonates, calcium carbonate, chalk, limestone, marble, all those substances are calcium carbonate, and you put it into an acid, Again, the carbonate will go with the hydrogen, or will it? And the calcium, the calcium carbonate, I meant to go further, or will it? And let's do the chloride. The chloride, use a different color, the chloride will go with the calcium now instead of the hydrogen. Hydrochloric acid, hydrogen chloride, gas, dissolved in water to form aqueous hydrochloric acid, now is combined with the chloride. And of course, you need two of them because calcium's a group 2 metal. It's always a +2 ion. And the chloride is what? Group 7 halogen, always -1. So I need 2 -1s to balance the +2. And so when I mix calcium carbonate with acid, it does dissolve. And this is a test. If you take geology, you add a little hydrochloric acid to your limestone or to your rock to look for bubbles, because this gas is what we call evolved or given off. You get little bubbles appearing in your solution if you put a drop of hydrochloric acid onto a piece of limestone or marble or chalk. And here's what happens. And notice I also made water. And these two H's combined with, so calcium formed calcium 2 plus CO3, CO3 2 minus. Well, really, this is a gross simplification of our equation, because after that dissolves, this CO3 2 minus reacts with 2H plus to form CO2 plus H2O. So this chemical equation is the overall chemical equation and doesn't always reflect side equations or intermediate steps. It only gives you the beginning and the ending products. Okay? So it's a simplification. It doesn't say anything about the mechanism or the route to get here. Now, here's sodium bicarbonate, but I'm supposed to call it sodium hydrogen carbonate. You know it as sodium bicarbonate or sodium bicarb or baking soda. Let me change colors. There is sodium bicarbonate. When I mix it with hydrobromic acid, I make sodium bromide dissolved in water. Again, plus CO2 plus H2O. And this gas is given off and is visible as bubbles in that gas-forming reactions. I only mention this because in these gas-forming reactions, if you remember, I said there are 3 ways we can tell if a reaction has occurred. Okay? One is if a precipitate forms. One is if a gas is driven off. And one is if you have a change in color. There are other ways you might feel something get hot or cold. Usually those exothermic, endothermic reactions may just be dissolution reactions, for example. But there are many reactions that occur that you can't visualize. But if you can visualize one of these 3 things, a reaction must have occurred. Now here's an example where I make sodium sulfide with sulfuric acid, which, by the way, it didn't have to be sulfuric acid. A lot of sulfur in this reaction. And I make sodium sulfate. But I also make hydrogen sulfide gas, the smell of rotten eggs and kind of the smell of Pine Bluff some days. So This is a reaction a normal person would carry out in a hood, and that an enlightened society would carry out in factories and plants that scrub this out of their exhausts. But I will stop my soapbox politicizing of this reaction. So, that's a quick overview of acid-base reactions. Just know what an acid or a base is. There's actually a third definition of an acid-base. There's Arrhenius. There's I won't say a third type of acid or base, but a third definition for acids and bases. Acids can be divided into organic acids and mineral acids, or strong acids and weak acids, or proton donors or proton acceptors. And for us, we have Arrhenius acids. They donate H+. And Arrhenius bases. They donate OH-. Then we have the Bronsted-Lowry acids and bases, in which case we, for example, change our definition of a base to a proton acceptor, something that soaks up protons to remove them from solution so that the pH rises, just as if you'd added an OH group. And then later we're going to learn about Lewis acids and bases, which are defined by how the electrons shift in the types of reactions we're actually going to be talking about next. So look at assignment 4.2. Before you go on, I have some questions over just acids and bases. The answers will be obvious from both the PowerPoint and your book. And until then, I will say stay safe and see you in the next either video help session or video lecture. And by the way, as you work the assignments for these, I will be posting video help sessions a day or two after I post the assignment. Goodbye now.